Hello everyone, welcome back to our channel. We were discussing trigonometric functions of class 11th maths ncert. Now, you already saw this figure in the last class. Here we have considered a unit circle. With a unit circle, the coordinates of these points A, B, C and D would be 1, 0, 0, 1, minus 1, 0 and 0, minus 1. Let's consider the coordinates of point P are A, B. So the coordinates of Q will be A, minus B. This is one unit. In the last class, we proved that this point can also be written as cos x, sin x. Therefore, your A is equals to cos x and B is equals to sin x. As you can observe, in the first quadrant, A and B both are positive. In the fourth quadrant, A and minus B, A is positive, and your first x coordinate is positive and y coordinate is negative. So in both the first and second quadrants, your cos x here is considered the angle that is made by POA, and therefore this will be minus x, angle made by AOQ. Now, cos of x in the first quadrant is equals to x, cos x. Sin of x is equals to sin x. What happens in the fourth quadrant? Cos of angle. The angle made here is minus x over here. This angle's value, cos of minus x, is A. We know that the value of A is cos x. Sin of minus x, sine of the angle, is equals to minus B. We know that the value of B is sin x. So this will be equals to minus sin x. By this observation, we can say that cos x is positive in the first and fourth quadrant. Cos x is equals to positive in first and fourth quadrants. What about sin x? We know that if we take a point over here, say P dash, and if we join this, forming an angle, again, x with the negative x-axis. If we draw this line, this angle will be minus x, considered from the negative x-axis. Let this point be Q dash. We know that in the second quadrant, the coordinates therefore will be minus A and B. Your x is negative in the second quadrant and your y is positive. Here, the coordinates will be minus A, minus B. What happens over here? Your sin x, if you can see, this sin x is positive in first and second quadrants, B and B. B is sin x. This value B is positive in first and second quadrants, which means your sin x is positive in the first and second quadrants. We know that tan x is equals to sin x upon cos x. So for tan x to be positive, both sin x and cos x should have the same sign. Tan x is positive only when both sin x and cos x have the same sign. By observation, in the first quadrant, A and B, which represents cos x and sin x, they both have positive values. In the third quadrant, A and your x coordinate and y coordinate both have negative values, which means you have minus sin x and minus cos x. The opposite, minus cos x and minus sin x. So definitely tan x will be positive in the first quadrant and in the third quadrant. The tan x is equals to positive in the first quadrant and in the third quadrant. Cot x is 1 upon tan x. Again, it requires both sin x and cos x to hold the same sign. So it will also be positive in the same first and third quadrant. Now, cosec x, we know that cosec x is equals to 1 upon sin x. So cosec x will also be positive wherever sin x is positive. Similarly, sec x is equals to 1 upon cos x. So wherever cos x is positive, your sec x will also be positive. Which means cosec x is positive in first and second quadrant, and sec x is positive in first and fourth quadrant. This might look a little messier, so let's transform it in the form of table. Let's rewrite it in the form of a table. We have 4 quadrants, 6 angles, and 6 trigonometric ratios. First quadrant, second, third, and fourth. First value is sin x. Sin x is positive in the first quadrant and in the second quadrant. Rest quadrants, its value is negative. Cos x. Cos x is positive in the first and the fourth quadrant. Sec x. Sec x is positive in the first and the fourth quadrant. Cosec x. Positive in the first and the second quadrant. Tan x. Positive in the first and the third quadrant. Cot x. Positive in the first and the third quadrant. The rest of the quadrants, the values will be of the respective trigonometric ratios will be negative. This table is very important to understand angles in different quadrants, to understand trigonometric ratios of angles in different quadrants. Let's continue our discussion and discuss about the range and domain of these trigonometric ratios. So, sin x. Before that, let's discuss it with respect to the table first. That will be much more convenient. The circle, the diagram first. We know that in a unit circle, these values a and b, they hold values ranging from -1 to 1. That means the minimum value of a is -1. The minimum value of a is -1 and the maximum value of a is +1. The minimum value of y, the maximum value of y is y coordinate or b is 1 and the minimum value is -1. So we can say that a ranges from -1 to 1. Similarly, b ranges from -1 to 1. So you can hold any value between -1 to 1. Similarly, this can hold any value from -1 to 1 based on the position they are on the circle. Now, A stands for cos x and B stands for sin x in the figure. So we can see that your sin x value ranges from -1 to 1. Similarly, your cos x value ranges from -1 to 1. Now, what about x? You can place any value of x over here. X stands for the angle. The angle that we are placing over here can be anything from 0 to infinity or -infinity to infinity. So it can be any real value. So if you have an equation y is equals to sin x, your domain would be any all the values of x, all the values that x can hold, which are all real values. And your range will be all the values that y can attain by placing those x values. If you place all these x values, what is the value? What are the values that y can hold? So y can hold any value from -1 to 1. It will never exceed -1 to 1 interval. Also, the terms -1 and 1 are included. So you can write this range as closed interval -1 to 1. You can also write it in set builder form, but the writing it in interval will suffice. For y is equals to cos x, it will be exactly the same. Your domain will be all the values that x can hold, which is are all real values, and range all the values that y can attain by placing the values of x, which is again -1 to 1, because cos x also ranges from -1 to 1. Next, based on these values, and a little understanding from the last class, we'll come up to domain and range values of other trigonometric ratios. Let's start with tan x. Now we know that tan x is equals to sin x upon cos x. So y is equals to tan x. X is your x values are domain and y values are range. So y values means all the values that tan x can attain. Now we know that for tan x is equals to sin x upon cos x, your cos x should never be equal to 0. That means your x should never be equal to 2n plus 1 into pi by 2, where n belongs to integer. I'll go back to the last class for explanation of this part. Y is equals to tan x sin x upon cos x, where x can never hold this value. That means x can hold any value except for this value. So x is a real number, but not this number, because if you place this number, your tan x turns to infinity. So you can write this in a set builder form as domain is equals to domain of tan x will be equal to a set of all x such that x belongs to R, comma, x is not equals to 2n plus 1 into pi by 2, and where n belongs to z. What about the range? Range is all the values that your y can obtain. That means when you place all these values of x, what is the values of that tan x can attain? The thing is, tan x can attain all the values. So your range will be real over here. You can also get a better picture of this, how range got into R, by observing the first figure, which is your circle, but we'll discuss that in the next class. I'll come back to this as well. But by observation, we can say that tan x, the range of tan x will be R. Tan x can hold all the values. Now, the same goes for cot x. If y is equals to cot x is considered, then cot x is equals to cos x upon sin x. The only difference being x cannot hold any values which are equal to integral multiples of y. So now your sin x should not be equal to 0, which means x can never attain the value of n pi. Again, you can write it in set builder form. So domain of cortex is equals to a set of all x such that x belongs to R, x is not equals to n pi, and n belongs to z, integral multiples of pi. Now range, as in tan x, it will also hold all the real values. The last two trigonometric ratios would be cosec x and cot x. For cosec x, we know the formula, cosec x is equals to 1 upon sin x. Y is equals to cosec x is equals to 1 upon sin x. If this is equal to 1 upon sin x, so again your sin x should not be equal to 0, which means x should not be equals to n pi. Okay, so what would be the domain? Domain again will be equals to set of all x such that x belongs to R and x is not equals to n pi, where n belongs to z. What about range? Now range over here is can be understood with the help of some examples. We know that your sin x value lies between -1 to 1. Let's try and place those. Let's consider a number line and try and place those values and get the values we so obtain of cosec x. This is my 0 on the number line, -1 and 1. And this is where I'm plotting cosec x, or y, where I'm plotting y. Now, when you take sin x is equals to 1 by 2, what is the value of cosec x? The cosec x is equals to 1 upon 1 by 2, which is equals to 2. A value outside 1 in the positive range. If you place any fraction from 0 to 1, you cannot place 0. You cannot place 0. But if you place any value from 0 to 1, say 1 by 2, 1 by 3, 1 by 4, any such value, you'll always get a value in this positive range from here till infinity. If you place a very, very smaller value, say sin x is equals to 1 upon 0.0000001, 5 zeros. So definitely here you'll get cosec x is equals to 1, 1, 2, 3, 4, 5. This much bigger value. So the smaller smaller value you place in the denominator of sin in the denominator of your cosec x formula, which means the smaller value you take, the greater the value of cosec x will become, which means any values from 0 to 1 for sin x will lead you to all the values from 1 till infinity. At sin x is equals to 1, 1 upon 1 is 1. So cosec x will also be equal to 1. So you're including the point 1. For all the values from greater than 0 and -1, up to -1. So for this interval, including -1 and excluding 0, for this particular interval, your cosec x lies from -1 to infinity, to minus infinity, written in the opposite fashion, in ascending order. So minus infinity to -1, including the point -1. This can be written technically in the same manner. So let's write it and then write the range inside field of. So for sin x is equals to 0 to 1, your cosec x becomes equal to 1 to infinity. And for sin x is equals to -1, including the value of -1. -1 to 0, the cosec x becomes equal to round bracket minus infinity to minus 1, including minus 1. Understand infinity and minus infinity are always written in round brackets in interval form. So this thing can be combined for your range because your range is this value union this value, uniting these two values. Two intervals are equivalent to sets. So you do not add sets, you always unite them. Union of these two parts. So you can write it in the set builder form as range of cosec x is equals to a set of all y. We've taken the variable y because cosec x is y. All y such that y belongs to R. They are real values. But what's the condition? Y should be either less than minus 1, these values, or it should be greater than plus 1. Less than or equals to minus 1, or y should be greater than equals to 1. If you have any doubt in these concepts, you can ask me in the comment and I'll explain it to you again. What happens when y is equals to sec x? For y is equals to sec x, we'll again consider the number line and region. We know that sec x is equals to 1 upon cos x. Cos x also varies from minus 1 to 1. It's again a fraction and you'll get the same values. So if you place any values for cos x, which is from 0 to 1, including 1, you'll get sec x is equals to greater than 1, all these bigger values, which is including 1 to infinity. And if you place cos x is equals to minus 1 to 0, your sec x is equals to minus infinity to minus 1. Here also your sec x for domain, your x can never be equal to 2n plus 1 into pi by 2. So your domain becomes a set of all x such that x belongs to R, x is not equals to 2n plus 1 into pi by 2, and n belongs to Z. Similarly, your range becomes equal to a set of all y such that y belongs to R and y is less than equals to minus 1, y is greater than equals to 1. These values. Including these points minus 1 and 1. So this concludes your domain and range for all trigonometric ratios, along with understanding signs in different quadrants for trigonometric ratios. In the next class, we'll again try and understand how the values change. If you consider sin x, how the sin x changes if you change the value of your angle from 0 to 2 pi, thereby allowing us to obtain a graph or represent sin x in a graphical fashion from minus infinity to plus infinity. Similarly, we'll try and represent all the trigonometric ratios on graph. See you in the next class. Thank you.